So, friend, have you ever wondered why you don't just float away into space, or why an apple falls from a tree instead of rising into the sky? The answer lies in an invisible force that governs our universe: gravity. Gravity. It's more than just a word. It's a fundamental force that plays a critical role in how our universe operates. It's the reason why, when you drop a pen, it falls to the ground instead of floating away. It's why planets, including our own Earth, follow a specific path around the sun. Yes, all of this is orchestrated by gravity. This unseen power is always at work, pulling objects with mass towards each other. It's what keeps our feet firmly planted on the ground and the moon in our night sky. It's the silent director of the cosmic dance that we are all a part of. So gravity is all around us, but how exactly does it work? Let's delve deeper. Sir Isaac Newton was the first to formulate the law of universal gravitation, which describes how gravity works. This law, in its simplest form, can be represented by an equation: F equals G times M1 times M2, all divided by R squared. Quite a mouthful, isn't it? Let's break it down. Here, F represents the gravitational force, the invisible pull that objects exert on each other. G is the gravitational constant, a number that helps to balance the equation. M1 and M2, these are the masses of the objects involved. The larger the mass, the stronger the pull. Lastly, R, the distance between the centers of these objects. The further apart they are, the weaker the pull. It's a delicate dance of numbers and constants, a balancing act that keeps our universe in motion. Now that we know the equation, we can see how changing the mass of the objects, or the distance between them, affects the gravitational force. Imagine you have two objects of different masses. How does the mass of these objects affect the gravitational force between them? Let's break this down. It's all about Newton's law of universal gravitation. According to this law, the gravitational force between two objects is directly proportional to the product of their masses. It means if you increase the mass of one object while keeping the other constant, the gravitational force between them also increases. For instance, consider a small object like an apple and a massive object like the Earth. The gravitational force between them is much stronger than between two apples. Why? Because the Earth's mass is immensely greater. In essence, the heavier the objects, the stronger the pull of gravity between them. This fundamental principle explains why you're pulled towards the Earth and not the other way around. So, the greater the mass, the greater the gravitational force. But what about distance? Does it have an impact on gravity? What if we keep the mass of the objects constant and vary the distance between them? How does that affect the gravitational force? Well, here's where things get interesting. The gravitational force between two objects actually follows what's known as the inverse square law. This means that the force of gravity decreases as the square of the distance between the objects increases. Imagine two planets. When they are close together, the gravitational pull between them is strong. But as the distance between them doubles, the gravitational force doesn't just halve, it becomes a quarter of what it was. If the distance triples, the gravitational force becomes a ninth of the original. You see, the gravitational force weakens dramatically with distance, and it does so in a predictable mathematical way. So the lesson here is simple yet profound. The farther the objects, the weaker the gravitational force. Now let's see how these principles apply in the real world. Gravity is not just a concept in physics textbooks. It has real-world implications that affect our daily lives. Let's consider the tides, for instance. The gravitational force between the Earth and the Moon is responsible for the ebb and flow of ocean tides. The Moon, though smaller than Earth, exerts a gravitational pull on our planet. This pull is strongest on the side of Earth facing the Moon, causing the water to bulge outward, resulting in a high tide. Conversely, when the Earth and Moon are at their farthest during lunar orbit, the gravitational force weakens, leading to low tides. Similarly, the gravitational force between the Earth and the Sun affects not just our planet's orbit, but also contributes to the occurrence of solar and lunar eclipses. Understanding how gravity works, how mass and distance influence it, helps us comprehend the celestial dance that happens in the universe every moment. So, the next time you see an apple fall from a tree, you know there's more to the story than meets the eye.